Welcome back, and in this video we're going to be looking at naming some aromatic compounds, and then we're going to be looking at the reactivity of benzene substitutes. We're not actually allowed to use benzene itself, as benzene is a class 1 carcinogen. So we're using methoxybenzene and methylbenzene to stand in the place of the benzene ring itself. So we're on page 7 of your notes, and we're just looking at naming these benzene rings. So we have here our benzene ring, and we have two ring substitutes. So we have a side chain and a functional group substitute. So let's draw out a few structures. 1,3-dichlorobenzene. So I'm going to draw my benzene ring, my hexagon, with my ring of delocalized electrons, and I'm going to put a chloro group on the first and the third carbon. Doesn't matter which way round I go round the ring, because I can always flip it over. So that's 1, 2, 3. Now there are some ones you're just going to need to learn. Phenol is one of them. So it has a benzene ring, but it has an OH group on the top of it, and that's actually going to change its chemistry quite considerably. We're going to study phenol later on in this pack. The next one we'll need to know is methylbenzene. So I've got benzene ring, and I've got a CH3 group on the top, and sometimes you'll see that called toluene. So 3 more structures for us to have a go at. Ethylbenzene is very similar to methylbenzene, except instead of having 1 carbon, I have 2 carbons. So I have a CH3 group on the end, and I have 2 carbons on the first, sorry, 2 hydrogens on the first carbon. Phenyl ethanoic acid has my phenol ring, and this time it has 2 carbons because it's an ethanoic acid. So you can think of it as ethanoic acid, which has had one of the hydrogens replaced by a benzene ring. Don't muddle it up with benzoic acid, which looks like this. It can get very confusing. Naming organic aromatic groups is a little confusing because that is phenyl ethanoic acid, whereas that is benzoic acid. I know, it's very annoying and it can get very confusing. 2-chloromethylbenzene is this structure. Because it's not in brackets, the chloro group is on the benzene ring, not on the methyl group. So I've got CH3, and then I've got my chloro on my second carbon. So that's 2-chloromethylbenzene. When you come to name them from the structure, they do give you quite a lot of leeway on this one, because it can get a little bit confusing why, for example, I said before, this is called phenyl ethanoic acid, but this one is called benzoic acid. So in this next little section of the notes, we're just going to be looking at the reactions of some benzene substitutes, methylbenzene and methoxybenzene. Okay, so we're on page 8 of your notes, and we're looking at the experiments with the arenes. So I've got methylbenzene, better known as toluene. I'm going to add a few drops of that to my watch glass. I'm then going to light it. You should see it burns with a yellow luminous flame and a lot of soot. It's a very, very sooty flame. The reason it's a very sooty flame is it's got a very high carbon to hydrogen ratio. So you can see there are lots of black soot being given off. So next we're going to look at the reaction between our methylbenzene and potassium manganate with some sulfuric acid. So I'm going to add a small amount of potassium manganate and a small amount of sulfuric acid to my test tube. So I want about equal amounts of both the purple potassium manganate and the colourless sulfuric acid. And you can see the solution there is a nice purple colour. I'm then going to add a few drops of my methylbenzene You can see it forms a layer on the top because it doesn't mix very well with water. So I'm going to give it a good shake. You should see that the manganate is not decolorizing. So this is different from the reactions with the alkenes. With the alkenes you would expect to see the manganate decolorizing. In this case you do not see any decolorization. Next reaction is with bromine. This is 10 to 12% bromine, so it's quite concentrated. So I'm going to be very careful with it. So I'm just going to add a small amount of bromine to my test tube. And then to that, again, I'm going to add a small amount of my methyl benzene. And you should see again there is no reaction. The bromine does not decolorize. Even though it's quite concentrated bromine, it still won't decolorize. Stays that brown colour. So for the last reaction, we're going to be looking at concentrated sulfuric acid. So I've got high concentration of sulfuric acid. I'm going to add a small amount of that to a dry test tube. So there you can see I'm adding a small amount to my dry test tube. To that, again, I'm going to add a few drops of my methyl benzene. You should see it there forming layers, and I'm going to give that one a good shake to mix the layers together. You should see the bottom is going slightly brown. There's no change still to the bromine and no change to the manganate. So I've got that brown solution being formed at the bottom. You can see it there in a little bit more detail. You can see there are two layers and the bottom layer has turned slightly brown colour. So we're on page 8, and as you saw in the video, when we burnt the methyl benzene, we got a very luminous sooty flame. It didn't react with our potassium manganate, in other words it stayed purple. Sometimes it slowly decolorized, and that's because methyl benzene is just slightly more reactive than benzene. Again, with bromine, even with that quite concentrated version of bromine, we saw no reaction. Sometimes again you'll get decolorization, but that's due to the free radical substitution of the CH3 group on the methyl benzene. So you saw the two layers with the concentrated sulfuric acid. The bottom layer was going a little bit brown, and again the methyl group makes the benzene ring a little bit more reactive than benzene. So comparing our methyl benzene with alkanes and alkenes, you can see that you get this very sooty luminous flame, but it doesn't react with any of the reagents that you would expect alkanes and alkenes to react with. So methyl benzene, like benzene itself, is unreactive, and it's down to that stability of that delocalized ring of electrons. If we now use methoxybenzene in place of benzene, methoxybenzene is even more reactive. So you are going to see some reactions with methoxybenzene because the oxygen, which is attached to the benzene ring, activates the ring. So in this case, you're going to see the bromine solution decolorizing, and we're going to get lots of amounts of steamy fumes as hydrogen bromide is evolved. In terms of sulfonation, you get two layers and you get that slight yellowing again that you saw in the first example when we used concentrated sulfuric acid. So the Friedel-Crafts reaction is a reaction we're going to study in a lot more detail, but it's the reaction with a chloro-bromo or iodoalkane. So we get copious amounts of HCl, white smoke, and the mixture turns orange-yellow solution. We can also nitrate it with concentrated nitric acid, and we get this deep purple colour developing when we warmed it. Now, the methylbenzene and methoxybenzene, much less reactive than the alkenes because, as we said before, of this delocalization. However, methoxybenzene is more reactive to both bromine and sulfuric acid compared to methylbenzene, and that's due to the oxygen on the attached to the benzene ring activating the ring. So that finishes this section of the notes, looking at the reactions of methylbenzene and methoxybenzene. And those are just standing in the place of benzene. You do, however, need to remember that both methoxy and methylbenzene are more reactive than benzene. So benzene would not react with concentrated sulfuric acid on its own. It wouldn't react with bromine or bromine water. So it doesn't do the typical reactions you would expect of a molecule with carbon-carbon double bonds in it.